Hello community! Today we are investigating how to override new knowledge, and we have some brand new research how to do this in a professional way. So let's start with this. It is easy. OpenAI ships here their proprietary LLM with this content here, and this is the shape of the moon, and you say, yep. And then I have a question. If I want to override this knowledge, because now my moon should have a shape like a shoebox, and now I want to calculate the gravitational field of the high tide in Dover, England. So, you see, now this is not a change of a single point of information, it will change the complete interconnected logical reasoning connectome in the LLM. How we do this in a professional way. Welcome to this video. And I would say, hey, this is a simple example, I know. But imagine Meta would ship their LLM with this content. This is the shape of the moon. Or, if you want to make it a little bit more spicy for my friends in the United States of America, you ask Meta, what are the achievements of the last 3 presidents? And maybe you do not agree with what you get back from the model, from the LLM by Elon, or maybe you don't agree with the LLM from Mark. So you see, sometimes you might find yourself in a position you want to change some particular content because you don't agree and you don't want to have the system in your system. And if I say, hey, I believe in science, and I think this is the shape of the moon, now you understand how to override knowledge in an LLM, and we have some beautiful ideas. Now, I know if I go out on the street and I ask 99% of the people that I meet, the standard answer I will receive is RAG. And you're right. Just look at the video. Just 3 months ago, we had a deep dive here into the anthropic implementation of a RAG system with contextual retrieval, with prompt caching and everything. Great. But you know what? Time moved on. Now, at the very last day of December 2024, here we have a brand new publication, and it is now about multi-agent filtering of retrieval augmented generation. Because you know what? They write here, just days ago, the existing RAG system frequently struggle with the quality of the retrieval documents, as irrelevant or noisy documents degrade the performance of the system, increase the computational overhead, and undermine the response reliability with RAG. So they say, hey, RAG is so, we have to improve it. And they had a new idea. And of course they go, 2025, with multi-agent filtering of retrieval augmented generation. And if you read my post here on my channel here just 12 hours ago, I give you more details about it. And I said, hey, this is actually quite a good idea. So you have, in addition to the re-indexer and re-ranker and whatever you have, now you add another 3 specialized, highly specialized AI system, specialized agent to improve the RAG performance. And you might say, hey, what a timely coincidence that just 2 days ago you presented us a new form of agents that are so easy to code. Look, this is it. This is the code agent. This is the complete code. And then just yesterday, you might say, you showed us here to build multi-AI agent system that are now absolutely perfect. Now we understand how to build this better RAG system. But it's not about the R, the retriever here. It is also about the augmentation, if you still want to go with RAG. Because think about it. The augmentation phase, it augments your original query with the extracted external data. So the shape of your prompt is now simply the query and more relevant information and knowledge. And this is what we call in-context learning. But now think about this. If I now want to change here a particular date, a particular fact here in the predefined knowledge of the LLM from Elon or whatever, and I want to change the date of birth of Mozart in this particular LLM, I can easily say, hey, I found out this is an incorrect date, please insert the correct date. Now, normally the LLM will not just modify this because you see, if I simplify a tensor structure here, the tensor weight structure here with a simple network, we just change here one single point of a fact. But you know what? If we now say, hey, I want to change the achievement of Mozart in the LLM, I now change here a complete sub-network, a complete sub-graph. And this sub-graph, it is not perfectly integrated in the rest of the graph of the history, of the time of Mozart, of the achievement of Mozart, where Mozart was living, the people Mozart met, cooperated. If this does not fit, I have a system that will hallucinate as hell. So therefore, the challenge of today is how to find the perfect mathematical methodology if I want to change the content of a predefined LLM. how I do this, that I still have the complete reasoning pattern of the old LLM, and everything was trained for I don't know how many millions of dollars, but I don't just want to change here a particular part, a particular subnetwork that is highly interconnected. If you think this is the reasoning connectome, how I change subconnectomes with other data. So you see, we are also in a RAG system, but we want more. So if you switch here between this and this, you see we have to care about the network topology, how we do this in an operational methodology. Now, I have here multiple videos on in-context learning, no more fine-tuning, unsupervised ECL plus, or scaling here the reasoning with multi-modal research for ICL for small particular LLMs, or how we do a visual in-context learning with the new methodology by Stanford. But today we have some new research. We can do it even better in context learning. So what we want to have to take here a standard LLM from Elon or whatever, and we say, okay, I'm happy with this. I just don't agree that the predefined knowledge, I want to change here minimal parts here of the network. So I want to override this knowledge with my belief, what I want to promote here with my LLM. And I don't want to start a new pre-training phase. I don't want to start fine-tuning. I don't want to invest any money. I just want to do it here. If it's a black box, show me the methodology to do it here. No money, black box approach. This is what we're going to talk about. Now, you remember when we had a look at this paper here, the geometry of categorical and hierarchical concepts in LLM. And you remember they talked about immediately formalize the representation of categorical concept as polytopes in the representation space. And we used then the formalization to provide a relationship between the hierarchical structure of the concept of the LLM and their geometry of their representation in their tensor networks. This already was amazing, but now we build on this insight. Or do you remember this study here? October 2024, not all language model features are linear, from MIT. And we talked here about, we believe that uncovering the true nature of models representation is necessary for discovering the underlying algorithm to use those representation. So there are something about this representation that we have to talk, and we have to have a deep dive into representation to understand those representations. Remember this particular paper that we look at Harvard University, MIT, and Cornell University. We spent quite some intense discussion on this for the world model. Remember? Building generative models that meaningfully capture the underlying logic of the domains they model would be really immensely valuable. And MIT tells us our results suggest new ways to assess how close a given model is to that goal. We will build on this insight also. So if you want to prepare for this video, maybe have a look at the paper in detail. But the main paper we're going to examine today is here, December 29, in context learning of representation. Harvard University, NTT, Harvard University, and University of Michigan on Arbor. And why it catched my attention? Yeah, we are talking about physics, intelligent, and AI. And this is my topic. So let's just define the terms before we start here. In context learning, ability of LLM to learn and adapt new tasks or new patterns by simply seeing a few examples within your prompt without requiring any update to the LLM parameters. There's no fine-tuning. Now, representation in LLMs encode knowledge about the world in the form of internal numerical representations, tensor structure, vector structure associated with each token. You remember the tokenization? And these representations are typically learned during the pre-training phase, and their relationship reflect the semantic connections. Remember the content that we want to map into a mathematical space, a vector space. And you might say, wait, this is not the real thing. This is so simplified. Hey, we can do better. We deserve better. Yes, so let's go here. Scientific. The process begins with a tokenization. We have our tokenizer breaking down the input text into smaller units. We call it tokens. Great. Then, tokenizer creates here a lookup table using the embeddings as a reference. And since the transformers don't inherently process here the sequences in order, we have our positional encodings here added to the token embeddings. And then the magic, if you want, of the transformer begins. Now, token embeddings, positional encodings, and then they are passed through a series of our transformer layers. And you remember from my other videos, in the layer we have our self-attention, the key mechanism here of a transformer, and our feed-forward network where we have the nonlinear activation function to really learn the stuff. But then comes the most important point, the residual stream in the architecture of a transformer. So the transformer layer output are not just the output from the self-attention and the feed-forward network. We are adding this to the initial embeddings to form here the residual stream at each layer, for each layer. And this, maybe you don't see it often in the visualization, this is an integral component of the success of the transformer, and it is crucial to understand in context learning. So the term representation that we find here in this literature, it focuses here on the activation within the residual stream of a very specific transformer layer that we will pick out of the architecture and analyze their content. Some further information if you would like to know. You remember that the vectors in the residual stream of our architecture are contextualized. So this means their values are not solely determined by the initial embedding at the start, but they are, of course, influenced here by the complete context of the entire token length context window that the LLM processes. And the specific layers the activations are extracted from. So this means each layer, you remember this from the classical architecture of a transformer, computes different aspects of the input of the query, and that the different layers capture different contextual information, also called features. If we build on this understanding, you understand immediately that now the residual connections are crucial. Since there's no fine-tuning, there's no pre-training, nothing. The tensor weights are untouched. We just have in-context learning. So our learning mechanism has to be different. And our learning mechanism is based on the residual connection. So adding the previous layer's output to the new transformation ensures that the model doesn't forget information about the original input. And this helps prevent here, and we had the problem of the vanishing gradient, this is also called the gradient problem here, in very deep neural networks. And this was the solution years ago. So each layer only learns to change a portion of this particular representation. Each layer is responsible for adding a small correction, or if you want, a refinement to the token representation in a particular mathematical space, building on what was computed already in the previous layers. The presentations are therefore not directly modified, but added, which is why it is important to track where the information is at any given layer if you want to optimize in-context learning. So this means that the information accumulates throughout here the residual stream. Remember, classical idea, shallow layers perform the basic operation, and the deeper layers may capture here the more complex contextual semantic relationship. And in this way, the information learned in the earlier layers is not lost as the token is computed in the deeper layers. So this residual connection is essential for complex reasoning. Just to make it clear, this is not a static encoding. I got a lot of comments here on those videos. No, we are here in a dynamic reorganization of the internal learning process of the LLM. So the gradual shifts in this representation within the residual stream across multiple layers, and this is now what reveals the development of the in-context learning representations. And by measuring now the representation, I will show you this how we do this. At each layer of the residual stream, this new research now shows us here the gradual overriding of the pre-trained semantics by in-context information in the deeper layers. And you say, hey, what? Here it happens. This is where the magic happens. The gradual overriding of the pre-trained semantics of your LLM by this new in-context information that we provide with our prompt, and this is now modifying here, especially for a complex reasoning task in the deeper layers. So we achieved it. We found exactly the place where it happens. Now, we have to do an experiment by feeding our LLM with a particular chosen sequence of token corresponding to graph traversals. I'll explain this in a minute. The self-attention mechanism causes now a reorganization of the token embeddings in the residual stream. And this particular reorganization is now detectable. is now visible with a tool. And this tool is simple here at PCA, demonstrating here the emergence of the graph topology. This is heavy stuff. And reading this the first time, I did not understood what this means. So remember, the self-attention mechanism allows the LLM to adjust here the residual stream representation of each token based on the relation it infers in the context window. But now we know where the learning in the eye is happening within context learning. Yeah, for my viewers who want here a visual guide, the real interesting question is, how is the learning happening in this transformer within context learning? Because if we understand exactly how the learning happens, the inner workings, we can now optimize the in-context learning. So, in short summary, short break, the representations are not just the token embeddings. A lot of people make this mistake, but the evolving and contextualized activation vectors within the LLM's residual stream of each layer. And we will examine each layer one by one. I'll show you this in 5 minutes. So the self-attention mechanism is now the main driver for the dynamic reshaping of these representations of in-context learning, allowing here our LLMs to learn new semantic roles in context. So not the single point of the date of Mozart, but its complete Mozart subnetwork. And this might also explain why the transformer architecture is so good at in-context learning. Let's come back to the paper, and you remember there was something about physics. Yes, let's focus now on physics. So let's do an experiment. So very easy. Here we have figure 1. This is the first figure, so we just start with this paper. We have here a grid, and this grid we fill in with words. Just words that we know that the LLM has a context, has been learned, has been trained on. And in this grid, we now put a specific code, a specific way how we go from apple, bird, milk, sand, sun, plane, opera. And it doesn't make sense, and this is exactly what we want. We want to have new data where we can be sure that the LLM has not been trained on apple, bird, milk, sand, plane, opera, but we want that the LLM learns this new information, this new knowledge. So you do this, and then you generate a sequence of tokens following a random walk on the grid, and this is the input to the contents of a Llama 3.18b model. And then you see, when is our in-context learning happening? Now look at this. And you might say, what is this? Now you understand immediately those are representation. Those are representation of our transformer architecture with different context length. 200, 400, 1400. And you might say, hey, wait a minute. This grid topology that we see here, what a coincidence. If I provide enough information, enough context length, 1400, this could look, if you are a little bit, it like a grid, no? Look, also the grid lines, this could be a grid. Now, understand what this is. This is not a visualization, what is really an object living inside the LLM. And I get a comment on my other videos. This is here a very particular projection of the representation from the residual stream activation in the layer 26 of our transformer architecture. And now the authors tell us, as the number of in-context exemplars increase, there's now a formation of a representation mirroring the grid structure underlying the data generating process. And you might say, this is not possible. That's what I said. So this data generation process, it was based on a topology of a grid structure where we defined with a simple random walk here a particular sequence. And you want to tell me that I can find inside the LLM, if I do here an analysis of the maximum variance of particular components with PCA, I can find a similar pattern, like the grid pattern, in a, if you want, visualization? I don't think so. However, the paper says, hey, it introduces here now a graph tracing task, just showed you, this is it, as a controlled way to explore here this in-context representation shift. And as you see, at a very short context, we have not enough data. This could be any geometrical figure. But this looks like a grid structure with grid lines, yeah? A matrix. So if we think about node, edges, and context, the node of the graph are represented by words that the LLM has likely seen before during the pre-training. Apple, bird, and so. The edges are the connections between the nodes defined by the graph structure. A square grid, a ring, hexagonal grid. The context is now the input to the LLM consists of sequences of tokens representing random walks along the graph, effectively specifying the graph structure without explicit labels or verbal description of this structure. So this is now an abstraction of learning happening. It is not just that single data are learned, but kind of a graph structure is learned. And you remember my example with Mozart. This is now kind of a subgraph topology that we see is now forming inside the LLM. And this is what we call learning. Now, we have a tool. We have here something very particular, our PCA, to reduce the dimensionality and visualize here the token representation in 2D. But you remember, the x-axis and the y-axis are very specifically chosen for here the variation in the data. So only if we have here the most significant axis of the variation in the data revealing here, it will reveal here the underlying structure of the representation of the original data. And if you think this is just happening in layer 26, have a look here at all the layers, 0, 2, 4, 6 to 30. You see that slowly, these grid lines are emerging. Layer 30 is already, could be identified as a grid structure. You say, okay, is this just llama? What about we go from a 1 billion to an 8 billion? Or we go to Google's Gamma 2 with a 2 billion and a 9 billion. You see, this seems to happen in the transformer models in general if we have some deep layers. And that's interesting. Let's do another experiment. Yeah? Now we position them not in a grid, but we position them in a ring. And then we generate some data. This is what should be learned. And now we have pairs of neighbors. Apple and banana. This is now a group, a tuplet. Orange and onion, those 7 and 6 are now a group, and you get the idea. This is now the data we want to learn in context learning. Let's have a look at this. If we have a very short context length and a larger context length, if we look now at the specific layers, in the later layers here, even if we go here to layer 26, if you have an extreme short context length, even 100 does not really bring out here the ring. But if you just go to a context length of 400, look here, layer 16 already shows here kind of a ring, and layer 26 even has some more information here. So those are the alteration of the representation in accordance with the context-specified semantics, the ring structure in our data, if you want a hidden pattern in our data. And this are now representations that emerge within our transformer architecture. Now let's look at this here, the Llama 1B, the Llama 3.1 8B, the ring structure for a Gamma 2 and a Gamma 2 9B. So interesting. Also other models seem to develop this. And now the authors say, as we show, increasing the amount of context, 100 to 400, leads to a sudden reorganization of representation in accordance with the graph's connectivity. And the authors go on and say, this suggests that the LLMs can manipulate their internal representation in order to reflect concept semantics specified entirely in context learning, in line with theories of inferential semantics from cognitive science. This is amazing, simply amazing. The deep neural network organizes in a form that there is, if you want, a sudden reorganization of a better optimal representation in accordance with the graph connectivity. It would make sense, no? It is something like an energy optimization if you think physics. This is absolutely amazing for in-context learning. And we say, okay, let's do this with a hexagonal structure. And yes, if we look, so again, this is the grid structure, this is the ring structure. And if you look at the different models, you see, yeah, you could identify also a hexagonal structure. A little bit of fantasy, you need a little bit of fantasy sometimes. But there is a hexagonal structure. So you're like, damn, this is really working. And you might say, but wait, these are just insights from computer science, And you might say, okay, but now we really want to understand this phenomena. We really want to understand how the learning is happening because we want to optimize our in-context learning. So we need now more powerful tools to explore here the inner workings of the transformer in reference to in-context learning, because now we are in 2025. So you might say, come on, we now bring in the big guy. Physics, complete mathematical physics. But this will be the topic of the next video, because I think we already had some excitement today in this video. So if you want to change your LLM content, if you want to override specific knowledge, like the form of the moon, to your preferred form, to your preferred predefined content, you don't want to accept what is given to you by Meta or Microsoft in their predefined AI system, but you want to make sure that it is according to your facts that you have, the beliefs that you have, the content that you want to generate, then maybe you have to modify the knowledge that is encoded in the standard black box LLMs. And you can do this with in-context learning, and this we're going to explore in mathematical details in the next video. I hope you enjoyed it. I hope you had a little bit of fun in this video, and it would be great if you subscribe, because then we will enjoy the next video.